Today's webinar is the first one this year in our US AMOC webinar series. Now I would like to welcome our presenter for today's webinar, Esther Brady, Project Scientist in the NCAR Climate and Global Dynamics Division. Esther is a member of the US AMOC Task Team 5 focused on Paleo AMOC. She is presenting today on investigating the role of AMOC in past climate change with coupled climate models.
Okay, thank you, Jeff. I was asked by Hallie Kilborn, the co-chair of Task Team 5, to present a webinar on a broad overview of modeling AMOC from a paleo modeling perspective. And for a 15 or 20-minute talk, that seemed a huge task. So I decided to focus on studies done mainly with the model that I'm most familiar with, the CESM and its previous versions. This is an outline of today's talk. I'm going to first present a little bit of motivation, and then give a brief introduction to paleoclimate modeling, talk about some of the responses of AMOC to paleoclimate drivers, giving some highlights from some modeling studies, a little bit about PMF 6 and PMF 4, and then talk briefly about advances in the next generation of Earth system models that will provide really great opportunities for paleoclimate modeling in the near future, and these final remarks. Okay, so first a little bit of motivation. This plot shows some records of climate change over the last 21,000 years, and it tells us important information about climate evolution. As climate came out of its cold glacial period and warmed from external drivers of enhanced northern hemisphere insulation, rising CO2 levels shown here. However, it also shows a rich millennial scale variability in some of these climate proxy records, punctuated cool and abrupt warmings and coolings, such as this cold period known as the Heimer-Stadial 1, and then a warming to the Bowling Warm period, and then another return to cold conditions in the Younger Dryas. So changes in the meridional overturning circulation have long been hypothesized as a leading candidate for bringing about some of this millennial scale variability. The MOC is an essential component of our climate system. It transports heat and fresh water, nutrients around the globe, and it's really important to understand its role in climate change. Models provide a consistent framework that can be used as tools to investigate some of the mechanisms that underlie these variations that we observe in the climate record. So this is just a schematic of the NCAR-based community Earth system model. It's comprised of different submodels, each representing a component of the Earth system's climate, such as the ocean and the atmosphere and the land and sea ice. We now can couple in a land ice model, and we have river models and land process models, and a coupler which is charged with taking care of all of the bookkeeping tasks necessary for computing fluxes between models on their different grids. So the models themselves are formulated to represent all the dynamics, thermodynamics, biogeochemistry, vegetation responses, et cetera, that we can resolve on the model grids, and then parameterizations for the subgrid scale processes that are unresolved. So for paleoclimate studies, we generally have to change the inputs to the climate model quite drastically. And these are the foreseens, both external drivers of the climate system, true foreseens such as changes in solar insolation and volcanic aerosols, plus other drivers of climate such as greenhouse gases, ice sheets, and meltwater that are not explicitly modeled, but would be considered slow responses or feedbacks over the longer time scale and need to be prescribed in our model. We also need to change boundary conditions such as the orography and bathymetry, land-sea mass, land surface properties, etc. So, oh, there we go. This figure comes from a paper that's an example of how we run paleoclimate simulations. This was a study that I did with Betty Otto-Gleesner and others at NCAR to simulate the response of climate to LGM climate conditions that were given to us as part of the PMF protocols. It's a static view. So these are equilibrium climate states, and what we found was that AMOC increased to LGM conditions with ice sheets closed Bering Strait, orbital for 21,000 years ago, and lower greenhouse gases, but decreased when CO2 was lowered, but everything else was kept at a pre-industrial state to glacial conditions, or CO2 is increased to a fourfold abrupt level compared to pre-industrial levels. So this presented some puzzles that a climate model can be used to try and understand why you get some changes that you didn't quite expect. However, it's a static view, and in order to understand transient climate change, one needs to do some transient studies. These were initially done in an idealized framework because freshwater additions from melting ice sheets were hypothesized to cause changes in the AMOC, the Atlantic Meridional Overturning Circulation. These made good idealized studies for climate models, and this is one that Betty and I conducted with our LGM climate state, where we applied a one-starter forcing for 100 years and looked at both the temporal response, shown here, and the spatial response. And what we found is AMOC declines through the forcing period with a slow recovery over the next few hundred years. However, Greenland showed a very rapid cooling in association with a very rapid rise and expansion of northern hemisphere sea ice, and looked more like the response of sea ice and less like changes in northern heat transport that would be induced by a decline of AMOC, a slow decline. However, this is an idealized study, and if we really want to understand the transient evolution of the last 21,000 years, we need to try to do the transient simulation, which is, shown here. This trace run, we call it, was simulating the transient response through the deglaciation, and this was a project led by Zhengyu Liu at Ohio State and Betty Otto-Gleesner. We used the CCSM3, an earlier version of the CESM, and all the transient forcings over the last 21,000 years. This figure shows also that we have some runs with single forcings through this time period, and these are really useful for trying to disentangle what mechanisms, what forcing climate drivers are causing different responses in the climate system. And I just listed a list of papers here that you can look at for further information about this run. You can also go to this website. And this data is available on the Earth System Grid. This is one study that highlights results from that run. If you hold the model at the LGM state and apply the CO2 greenhouse gas forcing over the last 21,000 years, you can see that over on the left, AMOC rises in response to a rise in CO2, apart from this last very abrupt response or abrupt change in CO2 and a very abrupt response, a decline in the AMOC in the historical period. So this is quite a different response than we think of when we think of response of AMOC to CO2. We usually think of a decline, and yet here through the deglacial period we saw a rise. In a study first authored by Zhang Zhu here in Climate Dynamics, he further explored this and found that the AMOC response to CO2 depends on the background climate state and the time scale. So initially, when you abruptly increase CO2 and double it to the LGM climate state or the modern state, you get a decline, like is shown over here, but then a recovery following that. And in the LGM state, we got a very vigorous recovery, and that key to understanding that different response was the sea ice ocean feedbacks, in particular the response of AMOC and sea ice, which is a lot more expansive in the LGM simulation, and thus the feedbacks are stronger. This model simulation result was also found in another modeling study from the MPI ESM, which also showed increasing AMOC to increase CO2 from an LGM-based state. So this is seems to be a robust response. Another study that we have conducted with the CCSN is looking at sensitivity to changes in Arctic gateways. And Aishu Hu has done a number of studies with many of the previous versions of CESM showing that when you close the Bering Strait in the North Atlantic and shut off the fresh water coming in from the Pacific, AMOC is enhanced. And northern heat transport is also increased due to the decreased freshwater transport into the regions where deep water formation is formed. He also showed in another study that this enhancement of AMOC promotes warming or melt conditions over the neighboring ice sheet margins, and suggested that this could lead to some really long-term cycle involving sea level, AMOC, and ice sheet melt, which would be very interesting to look at in coupled ice sheet climate simulation. For the Pliocene, we actually found that when we close the Arctic gateways in the warm Pliocene, which has a CO2 of about 400 parts per million, which is similar to present day, we got an improved comparison to the proxy data. The previous PLIOMIP-1 simulation with open gateways failed to achieve sufficient warming compared to proxy data, but new indications that the gateways were closed allowed us to have a better comparison to the proxy data. This leads me to talk a little bit more about PMF and modeling challenges for the paleoclimate situation. This schematic here shows what we call the PMF triangle, which illustrates the contributions to data model discrepancies. First, we have boundary condition uncertainty, like whether gateways are open and closed for a particular time period, or the magnitude and timing of meltwater, is very uncertain over the deglacial period. And then we have modeling uncertainties. We have model biases. We have perhaps missing physics, parameter sensitivities, and then data uncertainty, which we had a webinar earlier a while ago by Dan Amrine. And so reducing uncertainties in any of these regions allows us to achieve better data model comparisons. The other challenge with paleo simulations using these comprehensive Earth system models is that they often require very long spin-ups to get deep ocean close to equilibrium. They take a lot of wall clock time to complete long multi-millennial runs, and they generate a lot of output, especially these new models that are on the order of 1 degree horizontal resolution and like 60 levels in the vertical. There's hundreds of terabytes generated, and it requires many processor hours. And computer time and disk space is very limited. It's a real constraint in doing a lot of simulations. So the objective of PMF is to understand the response to different climate forcings, the paleoclimate states, very different from the present. This provides an evaluation of Earth system models and their ability to simulate climate change for out-of-sample climate conditions in comparison to the documented paleoclimate evidence. The PMF is actually part of CMIP, but only some of the simulations are CMIP runs as well. And those are the mid-Holocene and the LGM, which were the original PMF phase 1 simulations. And then the past 1000, which is the last millennium simulation, the last interglacial, and the mid-Pliocene simulation. There are also other runs that are part of PMF but not CMIP that some of the groups are choosing to do. And I refer you to the website and the paper here for more information about PMF. What NCAR has planned for PMF is shown here in the schematic. We have some existing runs from earlier PMF cases where we have the LGM simulated with the CCSM3 and the CCSM4, and we're about to start with the CESM 2.1 model. We have a last millennium ensemble with the CESM1 and a previous single case with the CCSM4. We have similar mid-Holocene simulations, that's for the LGM, and we're planning a transient Holocene simulation for the next year out or so. And also we're planning the last interglacial, which is a new run for PMF with CESM2. Also mid-Pliocene warm period and a transient deglacial, which is currently ongoing with the isotope-enabled CESM1. And this is a project with Cheng-Yu Liu and Betty Olive-Leisner. I just want to advocate for the use of large ensembles to investigate internal versus forced variability of the system. And that's part of what PMF does, although they're multi-model ensembles that we create with all of our simulations. But we, at NCAR, we have this large Millennium ensemble that's based on PMF 2, or PMF 3 forcings for the last millennium. And we have over 30 ensemble members now. And the plot on the right is a figure taken out of the BAMS paper where we document this ensemble, and it shows AMOC sea ice extent and the Atlantic multi-decadal variability SST index response to a composite, or the composite response to the 7 largest volcanic events in the LME. And I think in the interest of time, if you're interested, go to the paper and read more about that. Whoops, just 2 more slides. So I put together a slide here just documenting some ideas that for what we should expect in the next generation of Earth system models. Some models have some of these components already, but more and more models will be coming online for including these new advancements, which will be really great for the paleoclimate simulation. First, it just included biogeochemistry. This will give us a lot more understanding of AMOC and its role in the global carbon cycle, such as has been shown with models of intermediate complexity, like the study of Schmittner and Lund in 2015. And then we will be able to have more and more models with enabled with isotope tracers of the water and carbon cycle. And this will enable improved model data comparisons, will lead to better understanding of the underlying mechanisms in proxy climate records, and it will help evaluate the proxy climate relationships and how, and their stationarity. They're developed typically with the modern relationships in mind, and we can evaluate whether those work well for the paleoclimate conditions. Also, we will be having more and more Earth system models with coupled ice sheets, and this will advance new opportunities to model the interglacial climate change and compare to proxy reconstructions, and provide better predictive capabilities for the near-term projections of sea level rise and interactions with ice, sea ice and ocean processes that can be tested in a paleoclimate context. So to end, I just have a few thoughts. Earth system models provide a physically consistent framework to investigate mechanisms underlying the variations observed in the climate records. Coupled atmosphere, sea ice, ocean, or AMOC responses and feedbacks are critical to understanding AMOC variability and its role in climate change and its responses to forcing on all time scales. And I think we should try to incorporate more sea ice proxies into our reconstructions that we use to test our models, because it's, the feedbacks between AMOC and sea ice seem to be critical for some of the responses that we're seeing, and winds. Proxy data model comparisons are improved when models include more biogeochemistry and allow for a more direct comparison to the proxy record. And also the temporal response to a particular forcing can look very different at different latitudes under different forcings and for different components and AMOC-associated fields. And model simulations can help integrate a total picture out of that. So, thank you. I'll take questions.
Okay, thanks so much. Esther, we have one question right now in the chat. I'm going to read that out loud. How long are the Brady 2013 simulations? Do they drift significantly?
Yes, I would say there is a drift. I'll go back to the slide. You're talking, no, this one. You're talking about this, these simulations here. I think we ran the LGM on the order of 2,000 years. And yes, it depends on where you look. If you look at the surface climate, you don't see much of a drift. If you look in the deep ocean, there's drifts. And it's just so difficult, to run the deep ocean to a full equilibrium. And so, yeah, I would be happier with more years. The trace simulation, the start of that, the LGM condition, that was run for like over 5,000 years, and that was very well brought to equilibrium in the temperature and salinity of the deep ocean. And also the ideal age, that the start of the trace run was brought to like very, very good equilibrium.
Okay. Okay. Our next question is from someone who has their hand raised. I'm going to unmute Paola to ask their question. Hold on. Paola, go ahead.
Paola. My name is Paola Chessi. Hi, Esther.
Hi, Paola.
Could you please elaborate on what are the feedbacks, the sea ice feedbacks that lead to such a different behavior under CO2 increase in the LGM versus the modern?
Yes. First, the sea ice starting in the LGM base state is very extensive. It really comes into the subpolar gyre region. Like the Labrador Sea is almost completely covered with sea ice and starts to wrap around the subpolar gyre. The Nordic seas are partly covered with sea ice, and so it has much more extensive sea ice. And so when you abruptly raise the CO2, the first response you get is that warming response. So the surface density is lightened due to the warming, and sea ice starts melting back out of the region. Eventually, it goes away, and in the freshwater budget of the Nordic seas, where the deep water formation occurs, sea ice melt is no longer in the freshwater budget. And so a haline response takes over and really triggers this vigorous recovery at LGM and sustains it once the positive feedback between the AMOC and the sea ice is established. And for the modern case, the sea ice is not as extensive, and so that coupling, that feedback is just a lot weaker. And the Zhu et al. Paper has a lot of figures sort of documenting this that you could look at. He did a really extensive job looking at this in pretty good detail.
Okay, great. Our next question is from our chat box from Casey. Thanks, Esther. Is there an indication that last millennium AMOC behaves differently in the last 1,000 years of trace compared to past 1,000 simulation due to the much longer spin-up?
That's a really good question. I don't have an answer for you because I haven't actually looked at that. I suggest you email Zhengyu Liu, who might have looked at that. I think he has he's written some papers on the Holocene conundrum, where models don't seem to get that cooling from sort of the mid-Holocene that the data shows. Betty might have a good understanding of that as well. I haven't personally looked at that, so I can't say for sure.
Okay, great.
And that might be a really good, study too. I mean, the data is available, so it's out there.
Excellent. The next question, I'm going to unmute Malt, who has a question that they would like to ask.
Okay.
Go ahead, Malt, if you can hear us.
Sorry, here I am. Can you hear me now?
There, yes, we can hear you.
Yes, I had my own mute on here accidentally. Sorry. So this is Malte Jensen. I had a quick comment with regards also to the first question and how far those CCSM4 LGM simulations were equilibrated. Since we looked at that, we have a figure on that in Alice Mizoki's paper,
right.
Where I think it's pretty clear, and it's quite important to point out that while I agree that the SST is very close to equilibrium, the deep ocean really is not. And in particular, the strength and more importantly the depth of the AMOC, which is what we have some evidence for, is very clearly still showing in that model. which actually makes it more consistent with the proxy data, which is good news. And I think this is a really important point, that a lot of these models are not really run for long enough to achieve equilibrium in the deep ocean. And so the response that we see in the AMOC is very sensitive to often pretty ad hoc initial conditions. I think a significant difference between CCM3 and CCM4 can be attributed to the fact that one of them was spun up from a cold climate and the other one was spun up from pre-industrial. And so it's cooling. So yeah, I think that's a really important point. I actually wanted to say something else then, since Paula then asked the question, since I raised my hand. I think the CIs, you were talking about CIs in the North Atlantic. I mean, we have made a point, and others actually have made a point too, going back to Shin et al., when was it, 2003, I think. And I think the Klockman paper agrees with that too, is that for the increased CO2, changes in Antarctic CIs play a really important role in the long-term changes in the AMOC, not in the short term. The short term is definitely dominated from the north, but the long-term changes, I think Antarctic CIs is also playing an important role.
Yes. Yeah, the spin-up of the deep ocean is always a struggle. The limitations are real for having enough, wall clock time for one, because it takes quite a long time to run a 1-degree model. 5,000 years would take quite a long time. And
of course, this was not meant as a blame, to be clear. It's just
I know. I'm
it's
saying,
an important thing to keep in mind.
I agree with you, and I think it's the struggle has not, the issue has not been helped by having higher resolution models, and we haven't attempted any sort of acceleration techniques that we used to do in the early versions of the CSM. We used to have some acceleration techniques, and we weren't happy with those and what they did. So now we just sort of do a brute force spin up, and so maybe more research is needed to help in that regard, because I think you're right. I think, although no climate state is truly ever at equilibrium, even the LGM, but it might come closest to one because it was cold for so long, although there's variability even in that deep low. So.
Of course, but if we want to get that non-equilibrium part, we need to think really hard about our initial conditions, which we're not doing.
Right. Yeah. Yeah, it's one of the challenges, and that's why I think models of intermediate complexity can be more useful there, because they're faster. It could be run longer. I mean, longer model years. So, yeah.
Okay, great. Our next question is coming from our chat box. Hallie Kilborn asks, could you speak a bit about isotope-enabled models?
Yeah, I can show a plot, actually, which I reserved. I thought I had too much to show. This is a plot from a study led by Jiaxu Zhang, who's, I think, one of our participants here. And she's given a webinar on this study, I believe. And this is actually results from the isotope-enabled CESM ocean component that we developed initially, and now we have another version of the CESM, and we're working towards a version that we can run some PMF extensions with an isotope-enabled CESM2, but we're not quite there yet with the CESM2. But it gives you a more direct comparison in the ocean to the records, like the Delta 018 records, and if you have isotopic carbon tracers, the carbon, the radiocarbon, carbon-13 if you have a biotic ocean VGC component as well. And it doesn't get you all the way there with delta O18 because what you are measuring is the delta O18 in calcite, and that has a temperature component. But with offline proxy models, you can take the del O18 in the seawater that's predicted by the model and temperature and use some offline proxy models to make a better comparison with the record. And yeah, Joshu has done some work in that area to compare her transient simulation that she ran over the last deglaciation to some records in the North Atlantic. And they compared pretty well, I think. And then she went on to try and understand the signals in terms of what the model is showing about circulation changes and leads and lags in the warming between the northern water masses and the southern water masses that were formed. So.
Great. I don't see any other questions. If you do have a question, please raise your hand or type it into our chat box so I can review it. I'll give everyone a few seconds if there's any to raise their hands or chat, type in a quick question. Okay. Not seeing any questions. If there are none, I would like to just go ahead and thank Esther for taking the time to present today, and I appreciate everyone's participation. We will have today's webinar posted on the US CLIVAR YouTube channel soon, and if you have any questions, feel free to reach out to the US CLIVAR project office. Thanks again so much for everyone. Esther, thank you, and we hope everyone has a great day.